Hi class, welcome to the continuation on the lectures on quantum mechanics, and this is the start of chapter 7. And again, our reference is Introduction to Quantum Mechanics by David J. Griffiths, and this book is recommended, highly recommended for you. So in this chapter, we'll be discussing about variational principles, and this is a method in which you can get the maximum or the upper limit of the ground state of a certain quantum mechanical system. Now suppose we have the ground state energy Eg of a quantum mechanical system, and of course this Eg is of course described by the Hamiltonian, but this time we assume that the time independent Schrödinger equation is not yet solved. So in order to get the limit, the upper limit of the ground state, we have to pick in any normalized function psi. This could be anything, and we're looking for the upper limit, but it's not exactly the ground state energy would not be greater than that energy that we will be able to get. But there is also a question there whether that upper limit is close to the ground state. So we could try other normalized functions in order to get a closer value to the ground state. However, any wave function can be used in this method, in this variational principle method. So the expectation value of H in the state psi, presumably incorrect, is certain to overestimate the ground state energy. If psi is one of the excited states, then obviously the expectation value of H will exceed the ground state. But the theorem says the same holds for any psi. So let's see that later in some of the examples, but first we look at the proof of that. So since the unknown eigenfunctions of H form a complete set of solutions, then your psi can be expressed as a linear combination of them. So you have here this one here, where of course your Hamiltonian, when acting on the wave function psi n, it would also give the energy En. And so you have a linear combination of psi n as your psi. So psi is a normalized wave function, so you have this. So if you get the inner product of psi with itself, it should be equal to 1, but then you have a linear combination of psi n, and then you can take Cn out of the inner product, and if you put the Cn in this Cm, it would just be Cn complex conjugate of Cn, and if you take that out, it will just go back to Cn. And the Cm here, if you take that out, it will become the complex conjugate of Cm. So that's the rule. And since you have normalized psi n, then this would just be the Kronecker delta here. And so if n is equal to m, then your Cn square would be equal to 1. Meanwhile, when you get the expectation value of h, you also have to do this. So your expectation value of h would be that one, this one here, and this one you can also write as with a bar after h, or without the vertical bar. Is the same. So your expectation value of h would be then equal to this, equal to that. So we know that the ground state is the smallest energy of the system, and so anything would be equal or greater than that energy. So we have this, and hence we have the expectation value of h, which is just the energy you get with operating the h to any wave function, and that would just be greater, and always be greater or equal to the ground state of the system that you're looking for or you're considering. If the Hamiltonian admits scattering states as well as bound states, then we would have an integral as well as the sum if you want to calculate the energy. So let's go to the first example. Suppose the ground state energy for the one-dimensional harmonic oscillator is found to be if we find the ground state of a one-dimensional harmonic oscillator, then we will have to consider the Hamiltonian for the harmonic oscillator, which is this one here. So that's the harmonic oscillator Hamiltonian. And of course, since we've solved this in earlier videos, the ground state energy for this Hamiltonian would just be equal to this energy, which is 1/2 h bar omega. So we will pick a trial wave function this could be any wave function, but this time we will pick a wave function that is Gaussian. So here it is. We have that function, or you can write it also like this. So you have phi x. You can also write this as a e to the negative bx squared. So that's how you write it. So if you normalize this wave function, then you will be able to get A. And then so to normalize that, we have to use this. Which is just equal to the integral of psi star psi dx from negative infinity to positive infinity, and this is just this one here. So you're integrating this, and so that will just give you this one here, and of course your A would be given by this one, the amplitude of the wave function. So we'll proceed. So going back to the Hamiltonian, this is your kinetic energy, and this one is the potential acting on the particles. So you can get the potential energy by getting the expectation value of that, and you can get the kinetic energy by getting the expectation value of this operator. So your Hamiltonian is just the sum of the kinetic and potential energy expectation. So here you have that, here, here, and here. And so your energy, your kinetic energy, I mean, is just given by that. This is just this one, and you have that one. You can search the integral in I mean, you can, this is a common integral, and then you also have this one here for the potential, the expectation value of the potential. So all in all, you have, putting all this together, you have the expectation value of H. So according to the theorem, this expectation value here is of course greater than the ground state energy for any B, for any value of B. But we have to get the energy in which it's closer to the ground state. So how do we do that? We will get the extremum of the expectation value of H, or the E. This also equal to E. So when you get the derivative of H with respect to B, then you will have and then you will equate it with 0, and then you get B equal to m omega over 2h bar. And so if you put this one back to this equation, then it will give you this. The energy is just equal to 1/2 h bar omega, and this is exactly what's the ground state of the harmonic oscillator. We're just lucky that we have picked the right trial function. That's why it's equal. So it's the first case in which the expectation value of the energy, or the Hamiltonian, is equal to the ground state. Hamiltonian expectation value of the Hamiltonian of the harmonic oscillator with respect to other wave function, or the Gaussian function. But well, the Gaussian function is very easy to work with, and it's very popular to use. But later on, well, of course, the Gaussian wave function extends from negative infinity to positive infinity. But we can also use other trial functions, is which has a finite limit later on as we go through. So suppose now here, suppose we find the ground state of the delta function potential, which is we're supposed to find the ground state delta function of the the delta function potential here. So this Hamiltonian of the delta function potential, so this is the kinetic part and this one is the potential energy part. So again, we have solved this system, and the energy of this system is just equal to this. So we have shown the kinetic energy part is just the same as the previous problem, and then we calculate the the expectation value of the potential. So this is this one, and of course this is when you get the expectation value, this is just equal to this is equal to psi v psi, or this is equal to the integral from negative infinity to positive infinity of your psi times b psi star, dx. So anyway, we'll erase this, make this putting the mess away. So your expectation value for your V, your potential energy, would be this one, and then if you put them together, the kinetic and the potential, you will have H equal to that. And minimizing the H, we have here this one, and you have to equate it with 0, and then you get B equal to this, and then your B is actually equal to 2m square alpha square over pi h bar to the 4th. By the way, your alpha here is your strength of your delta function. So your minimum is this one, and this is of course greater than negative m alpha square over 2 h bar square, since pi is greater than 2. So any normalized trial function can be used. However, for discontinuous function, it takes some fancy footwork to assign a sensible interpretation to the second derivative as needed in calculating the kinetic expectation value of the kinetic energy. So let's proceed with example number 3 to illustrate that. In example number 3, we're going to find an upper bound on the ground state of one-dimensional infinite square wheel, which was given in chapter 2. And so we are now going to use a triangular trial wave function, not anymore Gaussian, which we used in the first 2 examples. So we will try a triangular wave function, which is given by this, where of course A we have to determine by normalization. So this wave function has two parts, from 0 to a over 2, and then from a over 2 to a, and so that your integral would look like that, from 0 to a over 2, which is given by this function, and then from a over 2 to a, which is given by this function, so that your a would give you 2 over a square root of 3 over a, where a there is just a constant, or a constant which is just the width of the well. So we will look at this. By the way, if you get the derivative of a, derivative of psi, sorry, this would just be, for this one you get derivative with respect to x, that would just be a, and this one would just be negative a, and so you have this, and therefore your derivative of the wave function, the trial wave function, is this one, given by, is plotted that way. Now but the derivative of the step function is also a delta function, so your second derivative then would be this one here. So finally, your expectation value of h would be given by this, as from here, here, and here. You have 3 delta functions, and so this one, if you evaluate this with this one, this will just give you integrate this one and this one, which is, okay, let's repeat it. If you integrate this one with this one, you get phi 0, and then this one and this one will give you this, and of course this one here and this one will give you that one, and then it will just give you this one here. Now for this problem, for this infinite square well, the ground state energy is equal to this one, and of course this is less than here, what's the result of our calculation. This is of course less than, this one is less than. So the theorem therefore works. We have shown that in this example the theorem works. So in example number 3, we didn't try a trial function that extends to infinity. Rather, we had a triangular wave function that extends at fixed points, only extends at fixed points. And here's the most important statement in this slide. The variational principle is a powerful and easy to use tool to find the upper limit, closest upper limit of the ground state of a certain quantum mechanical system. So the other important statement is that the only trouble with the method is the nearness of the results to the target, because only the upper bound can be ascertained and the technique applies only to the ground state. But is it only applicable to the ground state? We can solve problems to show that it could be applied to other states, not only the ground state, but in this particular in this examples that we have shown, we only applied it to the ground state. So we will apply the variational principle to solve the helium atom as well, because earlier in the previous videos that we have, we've shown that the helium atom has a certain energy, has a certain ground state energy, but it's way it's far from the experimental value of the said atom. So let's look at that immediately after this. But before that, I'll show you some problems which you can solve on your free time. So that's it. Yeah, there are 5 problems there. You can screenshot them and make some solutions if you have a lot of time. So we'll look at the ground state of helium. For the helium atom, you have 2 electrons in orbit, and these 2 electrons interact with a nucleus containing the 2 protons, of course with some neutrons. So the Hamiltonian for this system, if you ignore the correction, the fine structure corrections, you will have the kinetic energy, the supposed kinetic energy of the 2 electrons. For the first electron, which is this one, and this for the second electron. And then you have, for the potential part, you have the potential due to the first electron and the second electron with the proton, and the interaction of the 2 electrons. So you have 5 terms there. So we're now going to get the ground state energy of the helium atom, provided that the 2 electrons interact with each other. So it's measured experimentally that the ground state energy was equal to around 79 electron volts. The source of the problem is actually from the electron repulsion, which is this part of the Hamiltonian. If that is to be ignored, then you only have 2 independent hydrogen Hamiltonians. Of course, you have a nuclear charge of 2 electrons, and the solution would just be the product of the hydrogenic wave functions of the 2 electrons. and the energy would just be equal to around 109 electron volts, which is so much less than the experimentally measured value, which is around negative 79 electron volts. So you have this wave function where A there is the Bohr radius and the En is equal to negative 13.6 divided by n squared electron volts, which is the nth Bohr energy. Note that for a nucleus with atomic number Z, the nth energy would have to be changed to Z squared En, and your Bohr radius will have to be changed from A to A over Z. This is actually from problem in chapter 4. And the spin configuration associated with this one here is that the two electrons are antisymmetric, or the singlet configuration. So using the variational principle to have a good approximation of the ground state energy, let's pick up a trial wave function phi sub 0. The product of the two hydrogenic wave functions, ground state wave functions, and as you can see, it is an eigenfunction of most of the Hamiltonian here. So you will have this, and thus you have the expectation value would have to be this one here, and then of course you have your expectation value of the electron interaction as this one here. So you will have an integral which is just given by this one here to be solved for the electron interaction. So you have here, if we would put the R1 along with the z-axis, then this would be the positions of the two electrons here and here, and that your R1 minus R2 would be just equal to this one by cosine law. So in this positioning of R1, we would just be doing the integration by R2. So we will just if R1 is oriented on the z-axis, then R2 will just be the one to be integrated here. So you have R1 fixed in this axis, and R2 could be anywhere. It could be here and anywhere. So the phi 2 integral, of course, it could be anywhere. The R2 could be anywhere in space, so phi sub 2 could is integrated, of course, the whole space. That's equal to 2 pi, and then what's left is the integral of theta 2, and here's the integration of theta here. And so you have to change everything, like this one would have to be changed by this, and of course our d cube r2 would be this one, and of course you have the integral of phi 2 is just 2 pi, and then you will just have all in all. So for the theta integral, you will have just this, and you just multiply it with 2 pi to get the together with of course the integral of dr and dr2 and d phi 2, you will get I2, and then for the theta you have this integral, and of course this is just equal to that. You can always let the denominator here, you can let this thing here to be equal to some u, and then the thing inside us, the square root. So you can just let them to a variable, and then you will be able to get this. And then because you have R2 can be less than or equal to R1, then you have two possibilities here. This one, when R2 is less than R1, you have 2 over R1, and when you have R2 greater than R1, you have 2 over R2. So you will now have your I2 overall is this one here, if you put them all together, all the integral. So it follows that your expectation value for the electron-electron interaction would be this. So now for the R1 integral, the vector R1 integral, so it will just give you, for the angular integrals, it will just give you 4 pi, and for the R1 integral you will just get 5 a square over 128. So you can check on the math. You can actually just do this by variable substitution. So So finally you have this result. For that approximation, you have this result, and if you subtract that to the two hydrogenic wave function, the products of the two hydrogenic wave functions, then it will just give you negative 75 electron volt, which is very close to negative 79. But then again, 4 electron volts is still very large, so something more could have been done to make it closer to negative 79 electron volts. So we could do more and think more of a realistic trial functions other than phi sub 0, which is the product of two hydrogenic wave functions. So say for example each electron represents a cloud of negative charge, and this cloud partially shields the nucleus, so that the other electron will actually see an effective nuclear charge Z that is somewhat less than 2 as the charge of the two protons in the nucleus, because of the shielding or the screening of the nucleus by the cloud, the other cloud of electron. So this suggests that the trial wave function would have to be in the form of this one. So what is the difference of equation 7.27 with with 7.17? So let's go back. So we only used this function earlier. So instead of using z equals 2, we used 8 here, so that this is just now z cubed in 7.27. So, and also, so let's now check 7.27. So we have here z cube and the other 2 here, instead of interacting with the 2e charge of the nucleus, each electron would have to be interacting with the nucleus with z charge. So everything will have to be changed with z instead of 2. So our Hamiltonian will now look like this. It's a little complicated, but it's manageable. So here is our Hamiltonian now. So the first electron would interact with the nucleus with a total of z charge, and second electron would have to interact with the same nucleus charge. And then you will have here this one, and the interactions between the two electrons, and this one, and the interactions of the electron and the nucleus, and the interactions of the electrons themselves. So evidently the expectation value of H would have to be, or of the Hamiltonian would have to be this one here. So here the expectation value of 1 over r is just expectation value of 1 over r in the one particle hydrogenic ground state, but with this time with a nuclear charge of Z. So therefore your expectation value would have to be Z over A. So the expectation now of the electron-electron interaction would have to be given by this, except instead of 2 you will have Z. So multiply 2 over Z in equation 7.25. So everything will just be the same except that you're changing 2 with Z. So if you put them all together, our expectation value for H would be, or the Hamiltonian would be, this one here. And the lowest upper bound occurs when the expectation value of H is minimized with respect to Z. And so we will find out that when we derive the expectation value of H with respect to Z and equate it to 0, the Z would just give us 1.69. Indeed, for this value there is screening of the charge of the nucleus, so it's partially screened by the cloud of negative charge. So we are able to see how the charge 2 of the nucleus being screened just to show only 1.69 E of charge in the nucleus. So with Z equal to 1.69, it will give us an expectation value of H equal to this one here, which gives us an energy equal to negative 77.5 electron volt, which is much closer to negative 79 electron volts, and within 2% of the experimental value. So the ground state of helium has been calculated with great precision in this way. So what we just added with the previous one, which gave us negative 75, was that thinking that the nucleus is screened, the charge of the nucleus is screened by the cloud of the negative cloud of electron, so that the charge will not be equal to 2 but less than 2, which is 1.69. So if we if we do more readjustments, then we would be able to get closer to negative 79 electron volts. So that's it for this session. So you can solve the problems being shown here if you have time to solve them. So we've got problem 7.6, 7.7, and then the next one, in the next part of the series, we will be able to discuss we would have to discuss the hydrogen molecule ion. So it's kind of similar to the helium atom, but this time you have a hydrogen molecule. So we'll see what will be the analysis for that. So this is all for now, and I hope you've learned something from this first lecture of the chapter. See you in the next one.